We saw that U substitution was related to the chain rule, and it turns out that our second technique, integration by parts, is related to the product rule. So let's start by recalling what the product rule tells us. And another thing I'm going to do is, we talked about the idea of U before in our U substitution, representing a function of x, but simply writing U. I'm going to do the same thing here. I'm going to have two functions of x, U and V, but instead of writing that of x notation, I'm going to use the shorthand just U times V. So if I have a product of these two functions of x and I'm differentiating, the product rule says we take the derivative of the first times the second function plus the first function times the derivative of the second. And I can simply rewrite these or rearrange these terms to then write that U times V prime is equal to the derivative of U times V minus U prime times V. Next, let's integrate both sides with respect to x, and that's going to say that the integral of u v prime is equal to the integral of the derivative of u times v minus the integral of u prime v. Much like we saw before, this part here, the antiderivative of the derivative of u times v, that's simply going to be u times v. So to finish this off, again, just notation by noting that in a moment when I write du, that represents u prime dx. So that's like we saw in the u substitution video. And likewise, dv is representative of v prime dx. Then rewriting that last line above, I can say that the integral of u dv is u times v minus the integral of v du. So our strategy in this technique is to assume we start with an integral that can be represented like the left and then plan to rewrite it like the right-hand side. That's only going to be useful if the integral on the right-hand side is easier to solve than the one we started with on the left. So that's something we'll keep in mind when we're trying to use integration by parts. So a classic example where this is very useful is if we're integrating x times e to the x. I'll point out that a u substitution wouldn't really work here. If you try to make a choice of u, you'll kind of see that there's not anything that would lead us to being able to solve this. It is, however, a product, and I'll interpret this boxed expression up here on the left. We're envisioning this being a product of u times the derivative of v. So I have a product of two functions here, and my goal is to figure out which one should represent u and which one should represent the derivative of v. The more practice you get, the better intuition you will have for that. But I will go through two different choices here to see kind of what happens if maybe the choice you have here doesn't really work out. So to start with, let's let u equal x, and then the rest of this integrand, e to the x dx, we'll let be dv. Notice in our boxed expression, we need to be able to find both du and v. So once I make my assignment, on the next line, I like to find those other things. So if u is x, du is dx. Now, the antiderivative of e to the x is just e to the x. And I'll point out the process here. In this box, notice this box expression, I have u times v, so I kind of multiply along this diagonal, x, e to the x, minus the integral of v du. So then we multiply along the bottom here. So we don't end up using that top right expression on the right-hand side. So this becomes e to the x dx. I'll go back to what I mentioned before. Notice that the integral on the right-hand side, e to the x, is arguably simpler than that on the left, because we can at this point simply think of the antiderivative of e to the x. So carrying this through, I have x e to the x, and then minus the antiderivative of e to the x, which is e to the x. And again, because this is indefinite, I need to put a plus c there. So this would be my answer. And this would be an entirely correct approach to this problem. what I do want to address, since that worked, kind of how did I know to let u be x and dv to be e to the x? What would have happened if we swapped that? So what would happen if we had switched our choice of u and dv in the beginning? So if I started this and said, let's let u equal e to the x and then dv equal x dx, then du would be e to the x dx and v would be x squared over 2. So then in that instance, we would be able to say that the integral that we started with, that of x e to the x dx, is equal to, again, we take u times v minus the integral of v du. And the problem is, I don't know how to solve this integral. And arguably, that is not simpler, but in fact more complicated than the one we started with. We went from 1 power of x to the x squared there. So if I encounter this situation, this is when I would go back to the beginning and think maybe I could make a different choice of u and dv and try that. And again, as you're practicing these for the first time, there very likely will be times that you choose something that leads you down the wrong path. So being able to go back and try something else. The more practice you have, the more intuitive it will become in terms of like what a good choice would be. I do want to point out that what I've written here is a correct statement. It still follows from the derivation we have above. It's just not a helpful statement for my goal of trying to evaluate this integral. So as a general rule, to avoid, and again, this is somewhat vague, but my thought process when I am trying to use integration by parts is there's 2 things that go into my decision making here. So in general, I want to choose u and dv so that, first of all, u prime is somehow simpler than u. This refers to the example we looked at before. Notice in what ended up being a successful approach in our first part here, u was x, and then u prime, that was essentially 1 dx. So that is arguably simpler, whereas in the approach that didn't work, both u and u prime were e to the x. So that's not kind of simpler, it's equivalent to what we started with. And certainly we want to avoid something where we are making it more complicated. Now, something that we didn't have to deal with here, but we'll see in other examples, is we're also constrained by the fact that dv has to be chosen so that it is possible to find its antiderivative. As soon as I write down dv, I have to find v. So in this instance, choosing dv to be e to the x or x didn't matter. We could actually anti-differentiate both of those. But the second condition will show up in some of our examples, so we'll keep that in mind as another thing that can be helpful. And what I want to finish off with in this video is just what to do with definite integral. It's not quite so subtle as with u substitution, but I do want to point out the one thing I maybe see people do with this. So the idea here is just having bounds on the integral when we use integration by parts. So like before, what I want to do is use the same example we've already worked above, but throw on some bounds. So if I were starting this example from scratch, I would go through and find u, find dv, and use that process. But I'm taking advantage of the fact that we already did that. So we got to the point where we had this. So I think the main confusion I've seen with students in terms of the bounds is most people recognize, well, if the first integral had bounds from 0 to 1, so does the one on the right. And maybe the common mistake I'll see is that they'll end up with this function of x in their final answer. If it's a definite integral we're starting with, then I should end up with a numerical value. So what we have to consider is x e to the x, that's part of my antiderivative. So much like I'll do in the end, I have to evaluate the bounds of being those from the original integral. Now, at this point, you could evaluate the bounds on x e to the x and then find the antiderivative of e to the x and do that. Or, equivalently, I can hold off on x e to the x, find my antiderivative here, and then just put the bounds on the whole thing. Really doesn't matter. That'll end up in the same place. But in this case, importantly, all of these functions get evaluated at these bounds. So we would end up with 1 e to the 1 minus e to the 1. So that's going to 0. Minus 0 minus e to the 0. So we'd get, distributing that negative, we'd get a positive 1 here.